So this video is about how you could use Waits rule to find out the structure of boranes. That is, find out whether a particular borane cluster is closo, nido, arachno, or hypho, yeah, from the formula, and also to predict the shape of the particular borane cluster. Okay, so what would be the shape of the polyhedron? That you can find out using Waits rule. The way that Waits rule has been formulated, that is, we equate the find out the skeletal electron pairs and equate it to n+1. So we'll see that using examples. We will see in this case. First, let us take the example of a particular compound, say B5H11. Now this B5H11, how do you find out the number of skeletal electron pairs? The skeletal electron pairs is equal to, you know the formula, the number of boron atoms into 3, because each boron contributes 3 electrons, or each boron has got 3 valence electrons. So 3 into 5 plus the number of valence electrons of hydrogen, that is 11 into 1, plus charge if there is no charge here. So this is the total number of valence electrons minus the electrons that are taken for formation of BH bond. Since each BH bond takes 2 electrons, there are 5 boron atoms here, so 5 into 2, it is 10. So that is divided by 2. This will give you the total number of, when you subtract the total valence, subtract the electrons required for the BH from the total number of valence electrons, you get the skeletal electron, number of skeletal electrons or the framework electrons, and that divided by 2 will give you the skeletal electron pairs. So this is 15 plus 11, 15 plus 11, 26 minus 10, 16 by 2, that is equal to 8. So the number of skeletal electron pairs is 2. Now what we do is we equate this number of skeletal electron pairs, that is 8, to n+1. So here, if you look at Waits rule statements, all the statements, that is whether nido, closo, nido, arachno, or hypho, depends on the number of, the statement says n+1 skeletal electron pairs, plus we are looking at the number of vertices that are there. So if n+1 is equated to 8, then n will be 7. Okay, so n is 8 minus 1, that is 7. Now, if you look at this, a polyhedron with n is equal to 7, that is 7 vertices, would be a pentagonal bipyramidal. But if you look at the borane cluster, there are only 5 boron atoms. Or you can say this 5 is equal to 7 minus 2, or you can say the number of vertices in this particular borane cluster is n minus 2. So n minus 2, that is the 5 boron atoms. The 5 boron atoms occupying the 5 vertices, whereas 2 vertices are missing. So n minus 2 vertices and n+1 skeletal electron pairs, such a structure is arachno. And what would be the shape of the polyhedron? As I said, this is as a polyhedron with 7 vertices is a pentagonal bipyramid, but actually this has only 5 vertices, or only the 5 boron atoms are there. That means the structure of this borane cluster is a pentagonal bipyramid, pentagonal bipyramid with 2 vertices missing. 2 vertices missing. That means this is an arachno structure, a pentagonal bipyramid with 2 vertices missing. Take another example. Let us take the case of B5H9. Again, we calculate the number of skeletal electron pairs. That is 3 into 5 plus 9 into 1 minus 2n. 2 into 5, that is 10, divided by 2. So this is equal to 15 plus 9, 24, minus 10, 14 divided by 2 is equal to 7. Now again, like in the earlier case, we equate this 7 to n plus 1. So n is equal to 6. Now if you look at this, this is B5. That means there are only n minus 1 vertices in actual. So n minus 1 vertices and n plus 1 skeletal electron pairs. The structure is a nido structure. And how would you talk about the shape? You'll say S1 with, if all the 6 vertices were occupied with boron atoms, it would have been an octahedron, a closed octahedral cage structure. But here you have nido, that is what do you say, an octahedron with one vertex missing. Now, if you remember Wade's diagonal relationship, you can see when you look at the octahedral shape, the structure with same electron pairs, skeletal electron pairs, you see that if you have a six boron atom structure, you have an octahedron there. Again, if one vertex is moved from that, that is equivalent to a structure with one vertex missing, and you call that a nido structure. You should remember the diagonal relationship there. So here, using this Wade's rule, you're able to predict what is the type of cluster and also what is the shape of the particular polyhedron. So here you have an octahedron with one vertex missing. We'll look at another example again. Say B6H6 2 minus. Even otherwise, looking at the formula, because you have learned the general formula, you'll be able to say whether it is close or near or high for arachno. But this is how you calculate it or find it out by calculating how you correlate the skeletal electron pairs with the structure and the shape. So again, you calculate the number of skeletal electron pairs. This is equal to 3 into number of boron atoms is 6 plus 1 into the number of hydrogen atoms, that is 6, plus charge, that is 2, plus 2, you take it as plus 2, minus the 2 into n, 2 into n, 2 into 6, that is 12, divided by 2. So this is 3 into 6 is 18, plus 8 is 26, minus 12 is again 14, again that is 7. Now you equate this as n plus 1 is equal to 7. So n is equal to 6. Now this is, if you look at this number of boron atoms, that is 6. So that means this is a cluster with n vertices. N and the number of boron atoms are the same. So that means all the vertices are occupied by boron atoms. So the cluster has got n vertices and n plus 1 skeletal electron pairs. Now such a structure is referred to as a closed structure. Closed structure with the polyhedron with n vertices is a octahedron. So you can say a closed structure with octahedral shape. Okay. Now, looking at the n, we'll be able to say whether it is octahedron or octahedron with, or any polyhedron, let it be any polyhedron, whether all the vertices are occupied. You can say it is a closed structure with that particular shape. Otherwise, we look at it and see which are the vertices occupied, or how many boron atoms are there, and you say whether it is a with one vertex missing, 2 vertices missing, or 3 vertices missing. So we'll see what are the shapes associated with the number n. So if there are 4 vertices, we say it is a tetrahedron. If there are 5 vertices, we say it is a trigonal bipyramid. 6 vertices is an octahedron. 7 vertices is pentagonal bipyramid. Again, a cluster with 8 vertices is referred to as a trigonal dodecahedron. That with 9 vertices is a tri-capped trigonal prism. One with 10 vertices is a bicapped square antiprism, and that with 11 is an octadecahedron, and with 12, as we have seen, it is a typical, it's an icosahedron. So this is how we use it. Using 3 examples, I have illustrated how we can use, when again in the case of carboranes, when we study carboranes, I'll explain that. But here, using these 3 examples, I've showed you how you can calculate the skeletal electron pairs and find out from that skeletal electron pairs what the type of borane it is, that is whether it is closo or dido or arachno or hypho, and what is the shape of that polyhedron. That you can predict from using this skeletal electron pair. It's what I can summarize once again. You calculate the skeletal electron pairs using the formula, and then equate the number of skeletal electron pairs that you get there to n+1. From that you find out n, and then you look at the formula and find out whether the boron atoms corresponding to n are there, or it is less than the n that we have seen there. So depending on that, you say this is a particular polyhedron with, say it's a particular polyhedron, or it is a polyhedron with 1 vertex missing, or it is a polyhedron with 2 vertices missing, or it is a polyhedron with 3 vertices missing, and n+1. So in each case you write n+1 skeletal electron pairs. This is how you find out using the Waite's rule. Okay, so we'll